This chapter covers the following topics: schematic modular PLCs, inputs and outputs, and communication. Completion of this chapter will help you learn important PLC terms and develop an understanding of Siemens schematic S7 PLCs. Schematic modular PLCs are optimized for control tasks and can be adapted to meet application requirements by adding modules for power, inputs and outputs I/O, communications, and special functions. Siemens products in this category are listed as follows and shown in the accompanying figure: schematic S7 300, schematic S7 400, schematic S7 1200, schematic S7 1500, schematic ET200 with integrated CPU. Each of these PLC models is available in a variety of configurations and with many options. Schematic S7 300 PLCs have a space-saving modular design. S7 300 CPUs are available in Standard, Compact C, Failsafe F, and Technology T versions. Standard S7 CPUs range from the CPU 312 designed for entry-level applications to CPU 319-3 PNDP designed for the highest performance range. Some standard CPUs, like CPU 315-2 PNDP, shown in the accompanying graphic, have integrated Profinet and Profibus DP ports. S7 300 compact CPUs, shown here, have onboard I/O and technology functions. The specific technology functions included depend on the CPU model, but high-speed counting and pulse generation are examples of functions included in all models. S7 300 failsafe CPUs are used in applications where it is essential to guarantee the functional safety of machines or plants. They satisfy maximum safety requirements and comply with the relevant international standards. S7 300 technology CPUs have built-in features for motion control applications. S7 400 PLCs have high processing speeds and are especially suitable for data-intensive tasks, such as coordinating overall plants and controlling lower-level systems. S7 400 CPUs are available in Standard, Failsafe F, and High Availability H versions. Standard S7 400 CPUs range from CPU 412-1 in the medium performance range to CPU 417-4, which is designed for the high performance range. As shown in the accompanying graphic, S7 400 CPUs install in a rack along with other modules. S7 400 failsafe CPUs, including CPU 416F-3, shown in the accompanying graphic, are used in applications where it is essential to guarantee the functional safety of machines or plants. S7 400 high availability CPUs incorporate early fault detection features and diagnostic capabilities and CPU redundancy that minimize the probability of system failures. In the event of a CPU failure, the redundant CPU takes over the process. Schematic S7 1200 PLCs have a compact configuration and can be used in a wide variety of applications. S7 1200 CPU models range from CPU 1211C to CPU 1217C. All S7 1200 CPU models incorporate in a compact housing an integrated power supply, onboard digital input and output circuits, onboard analog input circuits, 1 or 2 built-in Profinet ports, and high-speed motion control I/O. A signal board, battery board, or communication board can be added to the CPU without affecting the size of the CPU. When additional I/O is required beyond what is available on board and with the addition of a signal board, S7 1200 CPUs except CPU 1211C allow signal modules to be mounted to the right. CPU 1212C permits the addition of 2 signal modules, and the remaining CPUs permit the addition of 8 signal modules. All CPUs have at least one built-in Profinet port. CPU 1215C and CPU 1217C have 2 Profinet ports, and all CPUs can be equipped with up to 3 communication modules mounted to the left of the CPU. All S7-1200 modules have built-in clips that allow easy and convenient mounting on a standard 35mm DIN rail. These built-in clips can also be snapped into an extended position to provide mounting holes for panel mounting. Signal modules have a bus connector on the front. Once a module is in place, the bus connector is moved to the left to allow the module to communicate with the CPU. SIMATIC S7-1500 PLCs provide extremely fast response times for optimal control quality and the highest system performance. SIMATIC S7-1500 CPUs are available in standard and failsafe F versions. Standard S7-1500 CPUs range from CPU 1511-1PN for small to medium-sized applications to CPU 1518-4PNDP for the most demanding requirements. The accompanying graphic shows CPU 1516-3PNDP. S7-1500 PLCs have a scalable configuration that incorporates a CPU, at least one system power supply module, multiple signal modules, and other modules as needed. The mounting rail can be extended to include up to 32 modules. All S7-1500 CPU models feature an attached display for commissioning and diagnostics and have built-in Profinet ports that permit the full range of Profinet communications, including the highest performance range, Profinet IRT communication, needed for advanced motion control applications. In addition, some CPUs also have 1 or 2 built-in Profibus DP ports. When additional Profinet or Profibus ports are required, or when point-to-point communications is needed, optional communication modules are available. S7-1500 fail-safe CPUs are used in applications where it is essential to guarantee the functional safety of machines or plants. Some SIMATIC ET200 systems, ET200S and ET200 Pro for example, can include an interface module with an integrated CPU. The addition of a CPU makes an ET200 a modular PLC. Using a distributed I/O station with integrated CPU relieves the central PLC of some control tasks and allows the central PLC to run a shorter, simpler program. At the same time, it improves the system performance by reducing response time for the distributed I/O station. When properly designed, this approach can also simplify troubleshooting. SIMATIC ET200S is a multifunctional, highly modular, compact I/O system. It has a rugged construction allowing it to be used in conditions of high mechanical stress. Interface modules for this system in standard and fail-safe designs are available with or without an integrated CPU. The interface modules with integrated CPU can be used both in standalone mode and for distributed automation solutions with a medium-sized program. Depending upon the version, Profibus DP and/or Profinet ports are available. SIMATIC ET200 Pro is a small, extremely rugged and high-performance I/O system with IP65, IP66, or IP67 protection. It does not require a control cabinet and can be mounted directly on the machine. Interface modules for this system are available in standard and fail-safe designs with or without an integrated CPU. The integrated CPU is based on the S7300 CPU 315-2 PNDP, is compatible with S7300 programs, and has Profinet and Profibus DP ports. role of the PLC's input-output I/O system is to translate the signals received from input devices into low-voltage DC signals that the CPU can use, and to perform the reverse operation when the CPU sends signals to output devices. In addition, the I/O system protects internal circuits from harmful voltage and current variations. A small PLC may have some or all of its I/O channels in the same housing with the CPU. For example, the accompanying graphic shows a CPU 1211C with 6 onboard connections for inputs and 4 onboard connections for outputs. This S7-1200 CPU model also permits a small signal board to be added internally for some I/O expansion, but does not permit the addition of external signal modules. Most Siemens PLCs, however, including the one shown in the accompanying graphic, allow signal modules to be added. Some or all of these modules may be close to the CPU, but signal modules can also be remote from the CPU. In addition, for large or complex applications, the number and types of signal modules is typically greater because the number and types of I/O devices required are greater. Examples of input devices used with digital signal modules are push buttons, limit switches, temperature switches, pressure switches, level switches, flow switches, photoelectric switches, and proximity switches. Some input devices use direct current DC, and other input devices use alternating current AC. The specifications for each device type also identify the level of voltage and current required by the device. An additional consideration when matching a digital input signal module to a DC input device is the polarity of current flow. Some DC devices are electromechanical, so the polarity of current flow does not matter, but other devices have built-in electronics that require a specific polarity of connection. For example, consider the S7-1200 PLC signal module shown in the accompanying graphic. This signal module is designed to work with 24 volts DC inputs and has connections for 8 DC input channels, 4 on top and 4 on the bottom. The accompanying graphic, for simplicity, shows only the top connections for this signal module. Note that this module allows the load power supply, which powers the input devices and circuits, to be connected with either polarity. The connection diagram shown on the left has syncing connections, and the connection diagram on the right has sourcing connections. The terms syncing and sourcing are designed to identify the direction of current flow, but because these terms are confusing, it's best to follow connection diagrams provided with the PLC documentation. Examples of output devices used with digital signal modules are lights, relays, solenoids, motor starters, valves, and heating elements. Some output devices use DC and other output devices use AC. 3 categories of digital output signal modules are AC modules, DC modules, and relay modules. AC output signal modules typically operate with a load power supply of 120 or 230 volts AC, or may be capable of operating with either source. These modules use a solid-state switching device, usually a triac, to control each output. This type of output works reliably with many AC output devices, but because a triac allows a small leakage current to flow when the output is off, it is not suitable for some AC devices. The accompanying graphic shows a DC output signal module designed to work with 24 volts DC outputs. This signal module has connections for 8 DC output channels, 4 on top and 4 on the bottom. And it is important to observe proper power supply polarity when making connections. The connection diagram shows the correct connections for the top terminals of the module. You may see the terms source and sink as it relates to DC output signal modules, but because these terms can be confusing, it is best to refer to the connection diagrams. Relay output signal modules offer the advantage of being able to work with either AC or DC devices as long as the devices operate within the module specifications and the switching speed required is not too fast. Each output on a relay output module is a set of relay contacts that close when the output turns on and open when the output turns off. The accompanying graphic shows a relay output signal module with 8 output channels, 3 on top and 5 on the bottom. The connection diagram is for the top connections on the module. The markings above and below the load power supply symbol identify the connections required. For a single-phase AC supply, L stands for line and N stands for neutral. The plus and minus connections apply if a DC supply is used. An analog input signal is generated by a sensor that provides voltage or current that can vary within a range, such as 0 to 10 volts or 4 to 20 milliamps. An analog input signal module converts the current or voltage to a binary value that the CPU stores for use in the user program. The number of bits in the binary value is referred to as the channel resolution. The more bits, the greater number of values that can be represented. The resolution available depends upon the module. For example, the accompanying graphic shows a signal module with a channel resolution of either 13 bits or 16 bits, depending upon the module version. Temperature measurement is an example of an application that requires special signal processing. Two types of sensors commonly used to measure temperature are thermocouples and resistance temperature detectors, RTDs. A thermocouple is a temperature sensor made from two dissimilar metals joined at a point called a junction. A thermocouple produces a small voltage that is temperature dependent. An RTD, also called a resistance thermometer, is a temperature sensor made from a metal such as platinum, nickel, or copper that varies in resistance in a predictable manner as temperature varies. There are various types of thermocouples and RTDs, and each type has different characteristics that determine its application range. Because thermocouple and RTD signals are different and require special processing, some Siemens PLCs have thermocouple and RTD signal modules. However, the S7-1500 PLC analog input signal module shown in the accompanying graphic can be used with a variety of analog signals, including RTD and thermocouple signals. When the CPU sends a numerical value to an analog output channel, the analog module converts the value to a voltage or current within the range set up for the output channel. The channel is typically connected to an analog output device that is controlling something in a machine or process, such as motor speed, valve position, or temperature. PLC analog output signal modules vary in the number of output channels, channel resolution, and output signal types. The module shown in the accompanying graphic has two analog output channels. These channels can be set up for either the -10 to +10 volts range or the 0 to 20 milliamps range. The output resolution is 14 bits for the voltage range and 13 bits for the current range. Signal modules have LED status indicators that are useful for system installation and troubleshooting. For example, the accompanying graphic shows two S7-1200 signal modules, a combination digital input-output signal module and a combination analog input-output signal module. Both modules have a status LED for each channel. The digital channel status LED is green and turns on when the input or output is on. The analog channel LED is green when the channel has been configured and is active, and red when there is a channel error. Both modules have a diagnostic LED that is green when the module is operational and red when the module is defective or non-operational. Multiple system power supply types are typically available for a PLC model to match the system voltage. System power supplies also specify a power budget, which is the available power that a supply can provide to interconnected modules. A load power supply provides power to input and output devices and channel circuits. In some cases, the load power supply also provides power to other PLC modules, including a system power supply module. Because input and output devices vary considerably in terms of their current, voltage, and power requirements, load power supplies come in a variety of types and capabilities. For example, the accompanying graphic shows a load power supply module for an S7-1500 PLC that mounts on the mounting rail with other modules. Siemens also manufactures a range of C-top power supplies for use with many types of equipment, including PLCs. A PLC I/O system can include components mounted near a CPU and components dispersed throughout a facility. PLC I/O system components mounted remote from the CPU are referred to as distributed I/O. Many Siemens PLC models are designed to use SIMATIC ET200 distributed I/O systems with network connections. These systems include some components designed for control cabinet mounting and other components designed for use without control cabinets. ET200 systems include ET200S is a multifunctional, highly modular I/O system. Interface modules with a Profinet or Profibus connection and with or without an integrated CPU are available. ET200MP is a scalable I/O system used both as centralized I/O and in distributed configurations with Profinet. ET200SP is a scalable and highly flexible distributed I/O system with a Profinet interface module. The version of this system designed for areas subject to explosion hazards is ET200ISP. ET200M is a modular I/O station for the control cabinet in high-density I/O channel applications. Interface modules are available for Profibus and Profinet. ET200 Pro is an especially small, extremely rugged, and high-performance I/O system. Interface modules are available for Profibus and Profinet. An ET200 Pro IWLAN version is available for wireless connection to a Profinet I/O controller. Interface modules are also available with CPU functionality. ET200 Eco is a compact block I/O for cabinet-free installation directly on the machine, and it connects via Profibus. ET200 Eco PN is a compact block I/O for cabinet-free installation directly on the machine, and it connects via Profinet. For Siemens SIMATIC PLCs, configuration and parameter assignment is accomplished using Step 7 engineering software, which was originally developed before TIA Portal and is now also available in TIA Portal. Step 7 Professional TIA Portal works with most modular SIMATIC S7 PLCs. S7 1200 PLCs can also use Step 7 Basic TIA Portal. Part of this configuration involves assigning unique identifiers to system components. There are various types of identifiers needed for different uses. For example, device addresses identify programmable modules with interfaces to a network. A type of addressing that is critical for signal modules is I/O addressing. I/O addresses are assigned automatically when signal modules are added in Step 7 and can be changed later if needed. The addresses of a digital signal module's inputs I or outputs Q are assigned in groups of 8, even if the module does not use all 8 channels. This gives every channel on a digital signal module a unique address that identifies the bits in the CPU's process image that store the channel statuses. For example, the digital input signal module shown in the accompanying graphic has 32 input channels. This graphic also shows the input address assignments for each channel if the module is configured as described. Because an analog signal module has a resolution of up to 16 bits, 16 bits are required in the CPU's process image to store an analog input or output channel value. As an analog signal module is added in Step 7, I/O channels are automatically assigned addresses. The first channel on the module is assigned the starting address, and the last channel on the module is assigned the ending address. For example, if an S7-1500 8-channel analog input signal module is assigned input byte 256 as the starting address, the channels will use the input bytes shown in the accompanying graphic. Step 7 allows the use of symbolic names referred to as tags associated with memory addresses. PLC tags are stored in the CPU's PLC tag table. Tag names can contain letters, numbers, and some special characters, and each tag name must be unique for a CPU. Use of tags helps when debugging a program or troubleshooting a system. The accompanying graphic shows an example of a PLC program network with the following tags assigned: Start 1, Stop 1, and Motor 1. Tags are shown in quotation marks in the Step 7 TIA Portal program editor. Instruction operands can also be displayed. Absolute operands such as I1.0, I1.1, and Q3.0 in the accompanying graphic are preceded by %sign. Absolute operands are available for use in any program block. Operands preceded by £sign are assigned to a specific program block. Step 7 TIA Portal software provides a variety of ways to monitor system operation if the programming device is connected to a CPU. This is useful for debugging a program or troubleshooting a system. For example, the accompanying graphic shows how a program network appears while being monitored in the Step 7 TIA Portal program editor with the push buttons in their normal state and the motor stopped. Note that the Start 1 and Motor 1 normally open contact instructions are shown in blue to indicate that they are open. The Motor 1 output coil instruction is also shown in blue to indicate that it is off. Next, the accompanying graphic shows how that program network appears in the Step 7 TIA Portal program editor while the Start push button is being pressed. Note that the three normally open contact instructions are shown in green to indicate that they are closed, and the Motor 1 output coil instruction is also shown in green to indicate that it is on. Finally, the accompanying graphic shows how that program network appears in the Step 7 TIA Portal program editor after the Start push button is released. Note that the Start 1 normally open contact instruction is once again shown in blue to indicate that it is open. Communication is central to what a PLC does. Therefore, understanding communication concepts is critical to understanding PLCs. PLCs communicate with many other devices and systems in various ways. In some situations, a PLC connects directly to another device. Often, however, various components of an automation system, including PLCs, are interconnected using network technologies. Serial communication is the most basic form of data communication used by PLCs because it involves transmitting data one bit at a time on a signal line and receiving data in the same fashion on another signal line, or in some cases the same line. A PLC uses serial communication with a variety of devices such as personal computers, printers, RFID readers, and barcode scanners. Serial communication uses interface standards such as RS-232, RS-422, and RS-485 that identify the signal lines available for communication. All three types of interfaces can be used for point-to-point communication. RS-422 and RS-485 also can be used for a multi-drop configuration with multiple devices connected on the same set of signal lines. Connecting a PLC to another device via an RS-232, RS-422, or RS-485 interface often requires a communication module. For example, the accompanying graphic shows S7-1200 communication modules used for serial communication. In most factories, the need for rapid information flow is critical. This often requires intelligent devices such as PLCs, drives, computers, HMIs, and some actuators and sensors to be interconnected by one or more local area networks, LANs. A LAN is a communication system designed for private use in a limited area. LANs are used in office areas as well as in manufacturing environments. However, LANs used in industrial applications must be able to operate reliably in conditions that are unsuitable for office equipment. Issues such as data rate, the number of devices to be connected, the reliability and noise immunity required, compatibility with other networks, and cost are examples of important industrial network considerations. Another important characteristic that defines networks is the network topology. The topology of a network is the pattern formed by network devices. Examples of network topologies include star, tree, linear, ring, and combined topologies. Some networks allow all of these topologies, and other networks are more limited in the types of topologies available. No single topology is best for all applications, so careful consideration should be given when choosing the specific topology for a network or portion of a network. A variety of cable types are used for industrial network communication. Two types of cables used for industrial Ethernet, including Profinet, are shielded twisted pair cable and fiber optic cable. Shielded twisted pair cable consists of twisted pairs of copper wires with a layer of braided wire between the outer plastic jacket and the interconducting wires to provide protection from external sources of electrical noise. Fiber optic cable is recommended for use in applications with high levels of electrical noise, where grounding problems exist, or where electrical isolation is needed. These cables are also used in open-air systems or where no electromagnetic radiation is permitted. Profibus networks also use various types of shielded twisted pair cables. AS interface networks, however, use a two-wire cable that carries both data and power. Wireless network devices send and receive signals through the air. Wireless networks are used where devices must be mobile or where it is too expensive or difficult to run cables. For example, the accompanying graphic shows a mobile panel that allows an operator or maintenance person to monitor a system without being tied to a control room. Wireless networks are also used where the controlled equipment must be mobile, such as with automated guided vehicle systems, overhead monorails, and cranes. One of the most popular types of factory wireless networks is IWLAN, which stands for Industrial Wireless Local Area Network. IWLAN uses devices with antennas to transmit and receive radio wave signals. There are a variety of antenna types used with IWLAN. This includes R-coax radiating cables, one of which is shown in the foreground in the accompanying graphic. R-coax cables are used as antennas from IWLAN access points. Openings in the outer conductor of the R-coax cable provide a defined signal strength along the entire length of the cable, enabling reliable radio links in areas where conventional antenna technology is impractical. For example, this unique antenna design allows R-coax cable to be laid in the rails of an overhead monorail track where standard antenna technology is very costly to install and maintain. Fieldbus is an industrial network used for distributed control, and the most popular Fieldbus is Profibus. The two most common forms of Profibus are Profibus DP for factory automation and Profibus PA for process automation. Both types of Profibus are open standards of Profibus and Profinet International. Some Siemens PLC CPU models have one or more built-in Profibus DP ports. Siemens PLCs also allow a communication module to be added for Profibus DP communication. Profibus is a master-slave system. The slave device communicates only when requested to do so by its master device. A Profibus master can control up to 125 slaves connected to the master in a linear topology. Profibus uses copper or fiber optic cables but infrared communication is also supported. Profibus has a maximum data rate of 12 megabits per second. Profibus has two classes of master devices. Most communication is handled by a Class 1 master, which is often a PLC. A Class 1 master controls all communication with its slaves. Most of this communication is handled through a cyclic polling process. A Class 2 master is used for configuration, maintenance, and diagnostics and can communicate with Class 1 masters and their slaves. AS Interface ASI is an open, low-cost network endorsed by the AS International Association that simplifies the interconnection of actuators and sensors with controllers. ASI replaces the complex wiring and proprietary interfaces often used with this interconnection with only two wires which transfer both data and power. ASI is most often used where actuators and sensors are distributed throughout a machine or facility. In an ASI network, a master communicates with up to 62 slaves through a cyclic polling process. The master is often a PLC with a communication module. The master, slaves, and 30 volts DC power supply are interconnected by the two-wire ASI cable. IO-Link is another actuator sensor communication system. IO-Link is an open communication standard developed by the IO-Link research group of Profibus and Profinet International in response to the need for a simple, low-cost way to allow actuator and sensor communication in a concentrated area, such as for a control panel or individual machine. IO-Link is a point-to-point system, not a Fieldbus. It uses a 3-wire cable, 24-volt DC power supply, and an IO-Link master. Depending upon the master, up to 16 devices per master are allowed. The accompanying graphic shows two examples of IO-Link masters and some of the many IO-Link slave devices that can be used with Siemens PLCs. Ethernet was developed in the 1970s to network office computers. As the use of computers increased in both the office and the factory, the need for common communication approaches led to the development of industrial Ethernet, which uses industrial switches to provide the performance and reliability needed for high-speed factory networks. An industrial Ethernet switch is an active network component that allows multiple devices to communicate simultaneously at high speeds. Industrial Ethernet allows communication speeds of up to 100 megabits per second with full duplex operation, which means that devices can simultaneously send and receive data. The Siemens SomaticNet product family includes Scalance industrial Ethernet switches designed to fit varied requirements from localized to plant-wide networks. Siemens also offers an extensive array of devices for interconnecting network components via twisted pair cable, optical fiber, or wireless signals. For example, Siemens Fast Connect system includes cables and connectors designed for demanding factory applications and assembly tools designed to speed installation. Profinet is the open industrial Ethernet standard of Profibus and Profinet International and the leading industrial Ethernet standard. Profinet I/O, the most widely used form of Profinet, extends the benefits of standard Ethernet communication to distributed field devices by simultaneously handling 3 communication performance levels. Non-time critical communication uses standard information technology protocols. Real-time RT communication works well for most control tasks. Isochronous real-time IRT communication handles the most time-sensitive tasks such as motion control applications. Because Profinet is an open standard, it allows field devices from many suppliers to be easily connected to the network. Profinet also protects investments in existing networks by simplifying their integration into a factory-wide network. The accompanying graphic shows an example of a few of the system types that can be easily integrated into the network. In a Profinet system, the number of devices is not restricted. Profinet uses copper or fiber optic cables, but also supports Industrial Wireless Local Area Network, IWLAN, communications. Devices on a Profinet network are connected through a switch. Siemens offers a variety of standalone network switches, and as shown in the accompanying graphic, many Siemens control devices have a built-in switch with one or more Profinet ports. Devices with two ports simplify use of a linear topology or a combined topology that includes devices connected in a linear manner. The following Profinet device types are shown in the accompanying figure: I/O controller, I/O device, I/O supervisor, and proxy. A Profinet system includes at least one I/O controller with I/O devices assigned to it. The I/O controller is typically a PLC or other control system which configures the I/O devices and exchanges data with them but does not control their communication. An I/O device in this context is not a PLC input-output device, but a Profinet-compatible electronic device that often allows actuators and sensors to be connected. An I/O supervisor, which is often a programming device, human-machine interface, or personal computer, is used for commissioning, monitoring, and diagnostics. A proxy is a device that connects a Profinet network to a Fieldbus such as Profibus. Because the proxy maps the subnetwork to Profinet, all the devices of the subnetwork are available for Profinet. These Profinet device types have been part of the standard since its inception. Later innovations to Profinet I/O include the following device types: shared device and iDevice. The shared device capability allows two I/O controllers to use the same I/O device. This is accomplished easily by copying the configuration from one I/O controller to another. The benefits are reduced costs for equipment, engineering, installation, and maintenance. iDevice is short for Intelligent Device. An iDevice is a local I/O controller that is also an I/O device for a central I/O controller. The central I/O controller has direct access to the input-output image in the local I/O controller, so communication is simple and fast, and no complex programming or additional communication hardware are required. Profibus and Profinet International PI has working groups with representatives from many companies, including Siemens. These working groups specify configurations of Profibus and Profinet devices that meet special requirements. The specifications are published by PI as profiles. Profiles are open and vendor neutral, allowing users to incorporate products from multiple suppliers into their systems without concern for interoperability. In addition to the Profinet I/O profile, which provides for the integration of distributed field devices via industrial Ethernet, examples of PI profiles are ProfiDrive, ProfiSafe, and ProfiEnergy. ProfiDrive and ProfiSafe were initially developed as Profibus profiles and later extended to include Profinet. ProfiEnergy is a Profinet profile. The ProfiDrive profile allows users and OEMs to design machines and processes with drives from multiple suppliers communicating via Profibus or Profinet. ProfiSafe is an integrated safety technology applicable for both discrete manufacturing and process automation, which permits the transmission of standard and safety-related data on a single bus cable. The ProfiEnergy profile enables the design of systems with controllers such as PLCs that can signal equipment, referred to as energy-consuming units, ECUs, to begin a sleep mode at the start of a planned pause or unplanned work stoppage. Software in each ECU determines how the sleep mode is implemented. When the sleep mode is over, the controllers signal the ECUs to resume operation. The use of ProfiEnergy configurations enables substantial energy savings without a reduction in productivity. This chapter has provided you with information on somatic modular PLCs, PLC inputs and outputs, and PLC communication. The concepts and terminology discussed in this chapter will be useful to you in furthering your knowledge of Siemens PLCs.